Um, Hello, everybody. Good afternoon. My name is Philip Cardiff from the University of Dublin, where I'm an associate professor at the School of Mechanical Engineering. So this talk is some of my initial steps into Cardiff's mechanics, electromechanics simulations. So this is, let's say, a first step in the project. So don't expect all the final racing Cardiff simulations. It's just to mention many co-authors about this. Okay, let me just remind you of the requirements. So it works back right side of your heart, and that's on top of your lungs, lungs. So it gets oxygen in your lungs, and it goes back. Left side of your heart, bigger, and left ventricle, bigger, stronger side, and that pumps it off the rest of the system. How does this work? So the thing driving it is the electrophysiology. So the right side of your heart, the SA node, it's the pacemaker node. This so frequency, maybe 1 hertz per second, it starts with the polarization cycle. So all these cardiac cells are all primed with a certain voltage difference. And then once this SA node sets them off, they start to depolarize, and then this spreads like a wave through the atria first. But then the atria are electrically insulated from the ventricles apart from a particular series of fibers. So then that brings this depolarization point down to the bottom of the ventricles. And then the ventricles will depolarize the bottom up. And then after they've depolarized, which is very fast, then they start to repolarize. So then slowly repolarize. So the entire depolarization might happen in 10 seconds. But then it takes like 1 second for the mechanical contraction. So there's a delay between the electrophysiology system. So what's going on here in terms of physics? So it's obviously coupled. We have the electrophysiology, that's driving the solid mechanics, or let's say the solid mechanics, they're contracting. That contraction is driving the mechanics. And then there's obviously interphysics coupling as well. So for the electrode to the solid mechanics, it's very strong coupling. This electrical depolarization causes strong RF deformation. But there is coupling back the other way. So the change in the motion, the stretch of the tissue change the conductivity or the electrical particles. But that's okay. And then there's strong coupling between solid and fluid parts. So it's broadly a mixture called an electrode cycle, electrofluid solid. So if I first talk about electrophysiology, how do people model this? So a common approach is called a biomedical. What is a biomedical? So if we imagine this idealized cardiac tissue, we've got cardiac cells, and then there's the space in between cells with extra cellular tissue. So what they mean by the bi-domain is these are our 2 domains, inside the cell and outside the cell. Let's just imagine this one. So we can pose a set of differential fluid mechanics equations, like homogenizing this later in terms of 2 unknowns, the voltage inside the cell and the voltage outside the cell. So the flow of current or ions inside the outside is governing this polarization. However, you can make some assumptions about the tissue properties inside and outside, and then you can get something like the monodomain model, so more simple version of the bidomain. And then you have 1 unknown, and it's called the transmembrane voltage. So this is just the difference in voltage. So rather than 3 independent voltages, you just have a difference in voltage. So it's just a scalar, high-level distribution of the tissue. We're not going to model itself directly. We're just using this quantization theory to get this high-level fraction. So what does this equation look like? Not this. It's the equation. I'm showing you this first, so you don't get scared. So this is plastic form. If you open up the plastic form, it's a diffusion rate. on the left, these are the journal. Right on the side. Fusion term, it's smooth things, and then you have a source. So rather than a diffusion equation, it's a reaction. So if you kind of the reactions, if you're comfortable with this, but if not, then you step through it. So we have a time term again, but again, transmembrane voltage at temperature. So confidence is very like practical. Confidence. So that's a conductivity tensor. So fibers in your tissue, so if you want to look at the fiber direction on fiber. So pretty similar. And the right hand side is the I external is an external influence. So for example, the pacemaker cells, they're like not that as an external influence, it's something like a set off. And then the only thing left to define here is I cell represents what's going on in the microtubular level, and they call these ionic parts. And if you go into this literature, as many ionic parts you want, more unknown for that. So if you want to implement the plastic phone, you can just copy the plastic phone, change the name called variables. So initially, and the simplest model I can find, it's the minimal model in Pittsburgh, Genoa, or with the high cell, it's a combination of three currents. That's massive current. So it's an average. And then economic currents are the functions which are not sunlight magnetic. So the H is against the biologists say we want to turn things on top. It's really not this. So you have these equations that give currents in terms of all these material parameters. It's a simple model. This is the simplest model, by the way. And then these really unknowns have S. These are called Dagen variables, some sort of scalar measure of ionic concentration. They're going by 3 photon's. So this is why it's a reaction. So it's ordinary differential equation. So some of the commonly used ones for ventricles have 20 photons. But you can get similar behavior. So how do you implement this in OpenFOAM? We just go to e-solvers and OpenFOAM. There's a nice system class, and if you derive from that class, then you can directly use the open solvers. There's only 3 pure virtual functions you can find. Equations, how many scalar equations of these are. Derivative, it's the right hand side, how you calculate the right hand side. And then I didn't bother finding Jacobian. Some of the OD solvers and stiff solvers are not participating in Jacobian. They don't have to. Okay, now how do I check if it worked correctly? So thankfully, there's lots of benchmarking papers, round robin benchmarks. So this is a common one, but so what they do is they give a piece of cardiac tissue. This is just a numerical case. And they assume it's all polarized, ready to be polarized. And then they just give an external influence like a tissue on. So I external, they apply it like a short fraction of a second. And that will cause polarization from all the tissue. And if we leave it long enough, and the benchmark, example effect mesh and stuff. So this voltage starts all negative, it's polarized, and it's polarized. So we're plotting the 0 voltage on the voltage. This happens in a fraction of a second. Now we talk what happens about this time. Activation time, how long it takes the wave to get to the point. And this is what the thing is. So if I run this large cells, 5 millimeter cells, it's the blue line. As I refine the mesh, green, red, the wave goes faster and faster. Eventually, so the wave speed is quite sensitive to the cell side. So in the paper, many groups all different codes in their answers using the same code. Both this behavior that we saw that is too slow for the course management, but then the confinement measures. Look at the code. Pretty A. I think is a spiral bucket. If I superimpose my answers on top of the other ones, they broadly impute. Now, in that case, they were using the more advanced ODE solver, so it's not exactly fancy. But it's and if you want to try this out, it's on GitHub. You just go to this GitHub here. So that's the electrophysiology. But okay, you can implement more ionic models, whatever flavor you want, but essentially that's the essence of it. The problem here is the physics of the electrophysiology. Very fine mesh, very fine step to get the wave of gift correct. And you want to much larger cells, much larger time steps for mechanics. So that's the challenge. So solid mechanics. So once again, thankfully, there are benchmarks in this area. This is the paper about years ago. They were trying to verify cardiac mechanics solvers. So one of their test cases is they call it idealized ventricle. It's like a parabolic ventricle, and it's a lot of the common cardiac physics. I think it's this ventricle. Once again, at round robin where everybody possible. So just to break down some of the challenges in mechanics, it's like so anisotropy is possible. I didn't really mention this, but this is the same anisotropy as in the electrode phase. The electrode phase, you have the fibers. There's higher than when the mechanics is different, it's like the opposite. But it's also spatially varying. So even the procedure to set the fibers has like a set wheels is a bit of a pain as well. But typically a heart ventricle, the fibers are kind of going upwards on the inside and on the outside, but then they go sideways, like wrapping around in the middle of the wall. That makes sense. So you kind of have it's like a pressure vessel in the line fiber. It's nicely designed. So then you have fibers going up and down, and this fiber distribution, and all that's put into the cell. How do they model this? So there's a variety of hyperelastic laws. So if you're not familiar with hyperelasticity, modeling like this, and essentially the way they do it, if you imagine a spring, a simple spring by this force displacement, and energy it's storing, and the triangle half base by height, so x by f by f is k and slope by x, half k by square. It's the area, that's the energy. So hyperelasticity laws are defined as energy, they want to strain energy. So it's a scalar function of how much energy is stored. So this is the tensions, this is how they do. But if you use this symbol here, remember, rather than x, they do it as strain, which is 3D. Not straining. You don't want to depend on x and y because they're arbitrary coordinate system. You have to do variance. It's invariant variance. So they get variance. So I won't like it. So in this case, the only law seems to use a lot. There's other ones, HCO, it's a lot as well. So in this case, very then you often need to use papers to do the differentiation yourself. So if you differentiate this scalar potential with respect to the strain factor, like component by component, you get stress. That's a definition. So you can do this on your lines. Stress. Now, the last part will be the passive mechanics. So it's just like rubber bands, you put the bar, look at the electrode, and then there are different ways to include the electrode, but they could be take the transmit potential, and then the function convert that into force in the fiber reduction. Fiber tension or a fiber shortening. They call one active stress on the inside. So this is active stress. You say active stress, and the passive one, and that pretty separate. It's fiber that just basically implies a scalar stress makes the fiber direction. So. And then for solving it, we can lift the green, find it out. Every flavor of every sun. So I'm going to look at a new flavor. I'm going to talk about it. And this is a point in the presentation where I run out of results. So this is more the picture. The benchmarking results. So they initially just take a small piece of cardiac tissue, fibers in one direction, and it's bending, and then this change bends correctly. Both for meshes, I'm not sure guys is here because I don't want to bring it. But this is a challenging. This is incompressible material, which is exception in solid mechanics as opposed to the rule, which is called locking. You get something called locking when you get 100% reflection. That's when you're getting further. Also, you get locking with the anisotropy, very highly anisotropy, that can also called locking. So you have to be careful when you design difference. And then towards this test case, they have two variants, one where they just inflated, and one where they inflate it, and then they apply an activation. They don't do the electrophysiology, they don't depolarize it, they just directly apply that TA. They just say, here's the tension, but here's the time. And because of fiber orientations, you get a rotation as it expands, it contracts, or you get a rotation. Makes sense. So that's kind of where I am at the moment. And then the final step, there's 4 papers in this area benchmarking. So there's one recent one, it's Stochi et al. And Hansen Nodal, they upload VTK mentions of bleeding hearts, but for the download, we're going to hearts. And you can put it in the go to so that's the next step, is to really benchmark full electromechanics, then towards the next step. Okay, comments on outlook, our next steps, more benchmarking, and then just one comment, I just want to get a new grant for this area, ERC grant, that'll start in January next year, so we're just working on topics like this. Thank you very much. What's the aspect, I guess. So let's say the application perspective, that's a grant is towards something called xenotransplantation, which is transplantation of animals. So I didn't talk about this here, but last year they put a big heart in it. So from a purely engineering perspective, shape and performance is different. So there's the geometry, even the aorta, when they sewed them together, it was half of the diameter of the universe. And they split, and they fixed the split. And the person was fine for a bit. There's just understanding the mechanics of that perspective. That's the application. But okay, you can do that with existing. So separately in parallel, there's a lot of CP codes that are fine about it. But if you look at, let's say, FSI code in this area, both for finding out monolithic, finding out through the gap, monolithic part. And so that's the gap that I able to bring, like say. And then some other extra blurry things like higher order. So, hi everyone. Hello everyone. Biomedical, Genoa.
And this talk is comparison between topological sensitivities for different dynamical applications. I want to start with an overview of the problem. So we work in the field of nasal flow, and why we do this? Because nasal difficulties, it's a problem, it's widespread, and it's a condition that clinicians frequently face, and they don't know. Sometimes they don't know whether the which kind of deformity causes the issue. So even when they do surgery, they rely on their experience, and for this reason, almost all out of the surgeries do not solve the problem. This causes a lot of useless surgery, and it's bad for the hypertensive systems. And in this field, it's difficult surgery possible. But difficult surgery is a surgery that is made beforehand during the actual surgery in order to evaluate the thickness of the surgery. And with the CT, this is possible. In this contribution, we'll compare two frameworks to evaluate the sensitivity of the operation with respect to some objective function that will decide. And the idea is to have a solution that can be given to surgeon in order to have a better idea on where to do surgery. Okay, so how can we evaluate the sensitivity? We decided to use the adjoint. So just briefly, even if yesterday we had talked about this, if you assume we have an optimization problem in which we have an objective function j life, the problem is controlled by some design variable, which is a vector of the length that we choose, depending on variables, and it's constrained by the state equation, which are in this case themselves. You can define this Lagrangian as the sum of these two terms. The first one is the objective function. The second one is the integral over the computational domain of some adjoint variable, which is a variable number, times the residual. This integral should go to zero, and we want the residual to zero on the side of the output. On the left, there is an picture that represents our computational domain. It's the upper gate. There is a sphere in front of the nose, and this choice was made to avoid stimulating the whole ambient, say, the whole box inside the head, which would be computationally dense, and it doesn't give those great improvement in the solution. So we use the sphere of the dimension that not prevents the deployment of the nose. Okay, since we want to evaluate sensitivity, so we want the gradient of how much the branch is affected by the design variable. We simply differentiate the Lagrangian with respect to the end vector, and this is the result. In the integral, since the residual depend on two variables, I would say it's like nested dependency to the a common practice to perform the integration is to use the Leibniz integration for integral variation, and that is the result. So we have, the most interesting part is probably the latest term that is called the Leibniz term, because different formulation of the joint treat is the term in different way. So in this talk, we talk about surface and topology optimization, and there are two different treatments. In literature, usually when we talk of surface optimization, we neglect the term. Neglect it because under the assumption that the residual is usually zero even on the boundary. And as you can see, this term is defined on the boundary. This is not always true, since as soon as we use coarse mesh, because of the boundary condition, this term is not actually zero. It's not really zero, and so it can cause some errors in the calculation. Why in the topological approach we do again the assumption that this term is zero, but this time we neglect the ratio, the derivative of the point well, depends of the point on the design variable. Why? Because on the top, in the topological optimization, the shape does not change some values aside. Okay, this is just to summarize how does those sensitivity work. In the surface, we have a heat map or a vector map on the boundary, which says which region should be pulled out of the machine in order to maximize or minimize the objective function. In the topological sensitivity, instead, the sensitivity is evaluated with respect to the momentum loss of the cell. So we have a map which says, okay, this cell is counterproductive for our objective function, or this cell is productive. Okay, the last step I covered derivative. It's the most important one. And right on the bottom, we have the three. Okay, two of them regard the surface integral, and the third one the topological. So as we said, the surface integral usually determines neglected, but in this work we'll use an improved version. It's called an ascendance integral, in which that term is evaluated. But there is some manipulation in order to be able to evaluate the residual on the boundary. Instead, in the topological, as I said, this term is zero. The two formulation, the surface and the topological formulation, differs only for a small term that is highlighted in red, and is a porosity alpha times the velocity. This term, alpha is the design variable in the topological optimization, and with the alpha we can control if the cell actually does actually flow or not. And with this, you can tune, can decide to solidify part of the domain if it's counterproductive. On the bottom, instead, we have it's the adjoint of the set of adjoint equation for Navier-Stokes, and even there you can find this term alpha times the objective function for this work is only the pressure drop. So we want to minimize the pressure drop in the upper areas in order to minimize the breathing difficulty if this is the case. Since the objective function is defined, as you can see, only on the boundary, the derivative of this function with respect to the flow variable evaluated, the volume is known. So those terms disappear, and the self-adjoint equation is the same despite the origin. Here you can see, I won't go into detail, but this is the equivalence equation. Tells how to move from the surface integral of the lattice term to the B term, so-called B term that is collimating. As you can see, it's evaluated on the linear domain. This term is much easier to evaluate, except for a single term that is not. It's quite tricky, and it's the last one, the derivative of its A with respect to the n, because this term should scales linearly with the number of design variables, since it must be evaluated with finite difference. To evaluate this, there are you can evaluate with finite difference, but there's another approach. It's called GDPD. In this approach, briefly, we use Laplace equation to diffuse the variation of the k, which are the coordinates of the point, with respect to the deformation of the boundary. So this is a much cheaper equation speaking, since we can do the adjoint also of this PD and add the Lagrange. Okay, here we can see the first results. The heat map in the figure, you see the green region, the adjoint is telling us that there is no sensitivity. Well, there is no change in the Lagrange with respect to the change of the shape. While where the blue appear, yes, that we have pulling, and in the red to pull out. The results are physically sensitive to us, since as you can see here, the throat, which is the region with the highest velocity, the adjoint is starting to make the pipe, the throat larger, And the same goes to other tissues, where, as you can see on the left one, the adjoint is telling us to make the pipe larger, the nostril larger. There are also some other regions inside of the domain which are not really easy to be seen, but that can give the surgeon some advice on where to move the boundaries. There is something else to notice here that is as you can see, there are some oscillation in the boundaries, some blue and red, like checkerboard oscillation, and we suppose that this is caused by the small oscillation at the actual geometry, and that the joint is telling us to make it smoother to reduce the losses. Okay, so these are the results for the first approach, the surface approach, and then we have the results for the topological sensitivity. In this, as I said before, you have as a sensitivity is the productive or the counterproductive cells are marked. In blue, we have the counterproductive cell, and in red, the productive cell. Results are quite similar to the previous one. You can see distributed. As before, the most counterproductive parts are the throat and the nostril, where the velocity is higher, and the other region, it's more or less tending to make the hole larger, but this makes sense since so far we use only the pressure drop as an objective function. Here you don't see any oscillation because the topological sensitivity is evaluated on the cells rather than on the surface. So it's not that sensitive to the shape of the boundary. Okay, finally, we use the third approach, which is the same as the topological sensitivity, but to take out the most from this approach, we gave the adjoint something to change in a closed domain. So we added the red box outside the nose, and we set the high value of porosity. This high value is set to prevent the air to flow there and to make this behave like a solid. While in the rest of the domain, we set the alpha equal to 0. And from this, I think we have the most interesting results. And as you can see from these two pictures, the adjoint is proposing us some topological modification inside of the head. And well, we have two. One is right one is a sagittal view, which is a plane that cuts the head out more or less, and the other one is coronal plane, which cuts in front. And we think that this is the most interesting result. So concluding, we have two different formulations of the joint that are compared using the same objective functions and boundary condition, and for what regards the inner part, the same mesh also. From this preliminary sensitivity, the formulation, we saw that surface sensitivity appeared to have some oscillation related to the geometry, which is quite tricky to mesh, and well, it's not that good. And while topological approach looks more robust, since I would say the sensitivity is set rather than physics. And finally, topological sensitivity with the pseudo-solid, as I call this pseudo-solid domain, allow for a much more interesting analysis and for much more effective advices for the surgeon in order to choose where to surgery. Okay, so where do they get the data? It's something they get, right? So, the first one was it? Okay, service data come from the CT scan. From this one, it's a patient from was not there for problems in the upper airways, so it's like healthy patients. And these CT scans are passed through a program which can generate the surfaces with respect to the absorption of the X-ray, since it's coming from the both of the body. So you can find like the threshold, and this software can build your boundary. And well, to make it more realistic if possible, this was made with some surgeons that told us, okay, it's the right shape. And the boundary condition in this simulation we used a flow rate inlet boundary condition. So we have a flow rate from the sphere, and well, the velocity field is evaluated like it's not uniform in the velocity. In the sphere, the velocity, so it's more realistic. We have only velocity per the velocity. To the mesh, I use the OpenFOAM package, so block mesh and stuff.